My name is Kazuo Yamada from National Institute for Environmental Studies, Japan. I am now charged in lead waste management after Fukushima Daiichi nuclear power plant accident. For the final disposal, we need to prepare a concrete disposal facility. So we have to think about the durability regarding to alkali aggregate reaction damage. So we need to develop a reliable testing method to assess the expansion potential of alkali-silica reaction. This AR-13 was established based on Japan Concrete Institute standard after active discussions in RILEM TC 258, avoiding alkali aggregate reaction in concrete with strong assistances of co-authors of the paper. Certain types of aggregate have caused serious expansion and cracking in concrete worldwide. These pictures show typical examples of alkali aggregate reaction damages. In serious case, reinforcement can be broken by the expansion of concrete. The reaction causing such damage is known as the alkali aggregate reaction AAR, named by Stanton in 1945. AAR is attributed to the alkali-silica reaction ASR, which results in the formation of alkali-silica gel with a larger volume than the original silica minerals. In order to detect the reactivity of aggregate, various test methods have been developed. The most simple one is a chemical method applied for aggregate. This method evaluates the dissolution amount of silica and adsorption amounts of alkali in alkaline condition. The second one is accelerated mortar bar test. In this method, aggregate is crushed to make mortar. Then mortar bar is dipped in highly alkaline solution at high temperature for 14 days. This is very popular worldwide, but not popular in Japan. Next one is a mortar prism test using a bit larger specimen, and accelerated with increasing alkali and addition, and cured at high temperature, right around 40. And it takes half or 1 year. More reliable test is concrete prism test. But depending on the type of standard, there are a lot of varieties of procedures rating aggregate combination, alkali boosting, temperature, and evaluation ages. And the most reliable is field exposure, using real job mixture and bigger size of specimen and for longer time. Alkali-silica reaction is caused by reactive silica, alkalis, and water, and alkali aggregate reaction expansion is caused by the alkali-silica gel being constrained by the matrix. The aggregate itself or surrounding cement paste, because the alkali-silica gel is viscous material, so without some constraint, it just flow out from the specimen. It requires some constraint to generate expansion. Therefore, to accurately test the risk of alkali aggregate reaction expansion, it is necessary to control the amount of alkali and water supply and use realistic aggregate sizes and combinations. In other words, concrete prism test of actual mixture is the only way to assess the risk of AR expansion precisely. For the acceleration of alkali-silica reaction, temperature and alkali content are increased. However, there have been one problem has been pointed out a long time. Expansions by CPT carried out in laboratory is less than the expansion in field exposure, as shown here. This figure shows the correlation between expansion in field for 7 years and the expansion in laboratory for 2 years. There is no unique correlation between them. Alkali leaching is presumed to be one of the key factors in reducing expansion in the laboratory. As an example, the results of comparison of the expansion behavior of specimens of different sizes are presented. One is a standard concrete cylinder with a diameter of 10 cm, and the other is a large concrete block with a dimension of 40 to 60 cm. They were manufactured using the same mixture and exposed at several locations in Japan. This conference is planned to be held in Lisbon. It's very unfortunate from Japan. It is almost impossible to visit Portugal now. Anyway, we exposed these specimens in different 3 places in Japan. One is placed at a coldest environment in Japan, like this. Then the others are warmer one, and in Okinawa, this is the warmest place in Japan. Two types of aggregate were examined. NT is reactive andesite, and EH is less reactive hollow fills. Greater expansion was observed in larger blocks, and faster and greater expansion was also observed in warmer regions such as Okinawa. But on the other hand, in smaller specimen, the expansion was very limited. The tendency is similar to larger block, but the expansion amount was much less, and the expansion is saturated in longer time. In lower pairs, the distribution of sodium in concrete was which was analyzed by electron probe microanalysis are shown. Warmer color, such as red or pink, indicate higher concentration. In the case of andesite in Okinawa, most of the sodium reached out from a depth of 5 cm after 5 years of exposure. This could be the reason for less expansion compared to larger block. So we need to control alkali content constant. Several methods has been developed to reduce alkali leaching. The RILEM AAR-13 attempts to reduce leaching by increase the specimen size from 7.5 cm square to 10 cm square in cross-section, and by omitting the sample cooling process during the measurement, which causes alkali leaching due to water condensation on the sample surface when the cooled sample is placed in a high temperature stage again. Such methods certainly reduce the amount of leaching, but the amount of leaching differs under different conditions such as storage temperature and the age of the measurement. Therefore, another simple method was developed. We proposed alkali-wrapping of concrete prism. Concrete prisms are wrapped in alkali-resistant moisture-retaining material and placed in humid chamber. The paper contains an alkaline solution with the same pH as the pore fluid in the concrete, depending on the total alkali content in concrete. At the timing of length change measurement, only water is supplied in order to control the alkali content to a constant level while ensuring sufficient water supply. In these figures, effectiveness of alkali-wrapping is shown. We examined by using various kinds of aggregate, but here two examples of different aggregate types are shown. TO is reactive andesite, and WI is sandy hollow fells. As you can see, TO showed almost similar expansion regardless of alkali-wrapping. Expansion tendency is a bit different, but a similar expansion was obtained with or without wrapping. However, WI hollow phase does not expand without alkali-wrapping, but does expand with alkali-wrapping. In this figure, mass gain, that means water absorption indicates, as you can see, by wrapping, sufficient amount of water can be supplied, but without wrapping, it is very difficult to supply water. Even specimens were kept in humid chamber. The relative humidity should be almost 100%, but there's a big discrepancy between direct moisture supply or humid condition. And lower figures shows the alkali leaching without alkali-wrapping or with alkali-wrapping. As you can see, different amount of alkalis are lost depending on testing conditions. However, by applying alkali-wrapping, we can control the loss of alkalis almost zero. It is then assumed that reliable test results for alkali aggregate reaction expansion can be obtained. Finally, I will explain about one application of this alkali-wrapped concrete prism test for expansion estimation. For the estimation, we use an equation. In this case, we use Bruno equation. By fitting this equation to the result of AW-CPT, like this, the dot the expansion test result in different two temperatures. By fitting this equation to the test results, every constant parameter used in this equation is determined. The temperature dependency was considered by Arrhenius law. From this test result, we have to consider something to estimate the expansion in field. One is the moisture supply, and the other is the variation of temperature. Moisture supply was based on the number of rainfall days, and daily change in temperature were taken into account. And as you can see, the expansion behavior in different places, one is coldest, warmest, hottest, warmest Okinawa, and middle Fukuoka. We can reproduce the expansion by this question. So this means, I believe, alkali-wrapped concrete prism test is reliable enough for the estimation of expansion. For further information, please visit my keynote lecture in coming International Conference on Alkali Aggregate Reaction, which will be held also in Lisbon at the end of May. Thank you for your attention.